Hi, today we go ahead to learn some of the topics of differential calculus. In that differential calculus, we have a lot of different topics. It may be polar coordinates, polar curves, angle between the radius vector and a tangent, angle between the two polar curves, pedal equation, derivative of arc, and the radius of curvature. In this video, I'm going to explain what exactly a derivative of arc. The derivative of arc means it's a part of the curve C, and the length of an arc of a curve is denoted by S. And in this, if there is a change in x from one point to another point, automatically the y value will also changes. If both x and y are changes, the length of the curve will also changes, and that is denoted as delta x. And the expression for this delta x can be obtained in three different ways. In the Cartesian form, we have the derivative of arc length represented by ds by dx, which is equal to 1 square root of 1 plus dy by dx the whole square, and ds by dy is equal to square root of 1 plus dx by dy the whole square. Next, in the parametric form, ds by dt will be equal to square root of dx by dt whole square plus dy by dt whole square. And in the polar form, we have ds by dr is equal to square root of 1 plus r square into d theta by dr the whole square, and ds by d theta, which is equal to square root of r square plus dr by d theta whole square. Based on this arc length, we introduce the one more concept called as the curvature. The curvature means here it's a part of some curve. For that here, we're going to define it the radius of curvature. That radius of curvature is the radius of the imaginary curve which is passing through only that particular curve. To derive this curvature or to obtain this curvature, we consider a general arc which is represented in any of the formats, maybe Cartesian, maybe polar, or maybe parametric. And we define it the curvature like this. The rate of bending of the curve C at any point P on C is called the curvature of the curve, and it is denoted by kappa. That we say here d psi by ds. The rate of change of tangent angle with respect to change in arc length is called as the curvature, where s is the arc length and psi is the angle between the tangent to the curve C at a point P and the positive x-axis. Based on this curvature, we can define the radius of curvature as like this. The definition is radius of curvature will be thus the reciprocal of the curvature of the curve at any point P is called the radius of curvature, which is denoted by rho. And rho is equal to 1 divided by kappa, or I can say this will be equal to ds by d psi. Where kappa is not equal to 0, always we take the rho is a modulus value, it's a positive sign only. From this, we're going to express the radius of curvature in a different formats that we will take it from one by one here. Now, we take the expression of radius of curvature in Cartesian form. To derive this, we consider a general curve which is in the format of y is equal to f of x. Then, here P is a general point on that particular curve, and A be a fixed point. Then S be the length of the arc AP, and phi be the angle made by a tangent to the curve at P, and psi is the tangent angle. And here, to derive this, we have the slope of the tangent is given by dy by dx, which is equal to tan psi, because psi is the tangent angle. But this dy by dx can also be written as y1 is equal to tan psi. That representation of dy by dx can be say it is y1. Similarly, if I differentiate on both sides with respect to x, then we have the y1 will become the second order derivative y2. And here the tan psi, first of all, we differentiate tan with respect to x means it's a secant square psi. And with psi with respect to x means this is d psi by dx. This expression can be simplified as y2 is equal to 1 plus tan square psi into d psi by dx, because the secant square psi can be written as 1 plus tan square psi. And this d psi by dx can also be written as by using a chain rule concept, d psi by ds into ds by dx. But we have the ds by dx can be written as the square root of 1 plus dy by dx the whole square, which is also equal to 1 plus y1 square whole to the power of from the derivative of arc length in the Cartesian form. By substituting these values in this equation here, we can simplify it to y2 is equal to 1 plus y1 square into and d psi by ds. It is a rate of change of tangent angle with respect to change in length. That is nothing but a kappa, but kappa is nothing but 1 divided by rho. And ds by dx will be equal to 1 plus y1 square whole to the power of half. And after simplifying for the radius of curvature, we get the rho value is equal to 1 plus y1 square whole to the power of 3 by 2 whole divided by y2. This is the expression for the radius of curvature in the Cartesian form. And this formula is very useful and very much important when you are finding the radius of curvature for the Cartesian curves.